Welcome to the second part of our lecture series on wind turbine modeling. In this section, we will describe the wind turbine drivetrain and its mechanical equations. This table provides descriptions and values of all parameters used in this section. As an introductory example, we use a one-mass model to represent the wind turbine. By applying Newton's second law to the mass in Figure 11, we obtain the dynamics in Equation 14, expressed in the International System of Units. The mechanical torque, Tm, produced by the wind is calculated from the mechanical power derived in the previous section. Here, we present a procedure for converting Equation 14 from the International System of Units to the per-unit system. First, we divide Equation 14 by the base torque. Then, by rearranging the parameters and defining the inertia constant, we obtain the dynamics of the one-mass model in the per-unit system. In this equation, all parameters and variables are expressed in per-unit values. The inertia constant is an important concept that denotes the moment of inertia in the per-unit system. The inertia constant has units of seconds and represents the time required for the mass to decelerate from nominal speed to zero speed when delivering nominal power without a primary power source.
A two-mass model is typically used to more accurately represent the mechanical system of a wind turbine. In this model, the turbine and generator are represented by two masses connected by a shaft. The two-mass system is modeled using a damped spring model. The model parameters are the spring constant and the damping coefficient, which represent the stiffness and mutual damping of the shaft, respectively. In addition to the mechanical and electrical torques applied to the turbine and generator masses, three additional torques must be considered: the elastic torque, the damping torque, and the friction torque. Elastic torque is proportional to the spring constant and the angle difference between the two masses. This angle difference is called torsion angle. Assuming the shaft operates within the elastic range, the relationship between torque and torsion angle is linear. Damping torque is a transient term that introduces the damping effect. This damping is proportional to the speed difference between the masses. Finally, friction torque represents rotational power losses.
By applying Newton's second law to the two-mass system in Figure 12, we obtain the following system of equations representing the dynamics of the wind turbine mechanical system in the International System of Units. The dynamics of the wind turbine mechanical system, expressed in per-unit values, is given by the following system of equations. These equations are obtained by dividing the torsion angle dynamics by the base generator speed and the speed dynamics by the base torque. Bars denoting per-unit values were omitted from these equations to simplify the notation. Since the turbine and generator rotor angles increase over time, the torsion angle gamma TR is used as a dynamic state in System 23 to preserve only the relative displacement information and achieve steady-state equilibrium.
After obtaining the equations that represent the wind turbine mechanical system, we must determine the model parameters, such as the spring constant and damping coefficient, to match the model response to that of a given turbine. A procedure for calculating these parameters is described below. The two-mass model can be written in matrix form, as shown in Equation 25. By using the state matrix in this equation, we can calculate the system eigenvalues. These eigenvalues provide information on the model response. The response of this mechanical system is mainly determined by the oscillation mode, given by the complex eigenvalues in Equation 26. The frequency, damping, and settling time of wind turbine mechanical oscillations can be obtained from the time domain response of field tests and recorded disturbances. This allows us to determine the eigenvalue shown in Equation 28. Then, by equating the real and imaginary parts of 26 with 28, we can find the spring constant and damping coefficient as a function of the turbine and generator inertias and the frequency and damping of the oscillation. In this way, we can represent the wind turbine mechanical system using a two-mass model with parameters given by Equations 29 and 30.
Now, we will describe the blade pitch angle actuator and its controller. These are the parameters used in this section. Figure 13 shows a block diagram of the control and actuator. The control is a proportional integral controller. In Figure 13, the controller input is represented by the error of a generic variable z. This variable is either the rotor speed or the delivered active power, depending on the control approach used for the wind turbine. These approaches will be explained later in the lecture. The actuator model incorporates the relatively slowed time constant, Ts, of the servo mechanism, as well as amplitude and change rate limits. Assuming no limitations and using block algebra, it can be shown that this model is equivalent to a first-order low-pass filter with time constant Ts, as shown in equation 31. To account for limitations, we must use the model given in equations 32 and 33. This model includes a limited integrator with signal u as the integrator input. See figure 13 for the location of signal u. The limited integrator logic is described by equation 33. Essentially, this logic states that the integrator is frozen by setting its input to 0 when the pitch angle reaches its minimum or maximum limit.
Equations 34 and 35 represent the proportional integral controller. Due to the presence of limiters, and anti-windup logic must be added when implementing this controller. This logic is similar to that of the limited integrator. Since this logic is used in several wind turbine control loops, it will be explained later along with guidelines for designing control loops. This control system automatically adjusts the pitch angle depending on the wind speed. This means that it does not require switching elements to operate properly under different wind conditions. This pitch angle control is widely used. More sophisticated schemes can be found in the literature. For example, reference 5 describes a pitch angle control that uses gain scheduling and is also commonly employed. In the next part of this lecture, we will discuss reference frame transformations used to represent three-phase circuits. Thank you very much, and follow us for more content like this.